The measurement everyone thought was wrong. At first glance, it looked like a mistake, a number that refused to fit inside the margins of what science considered acceptable. It appeared quietly in the data, unremarkable except for the fact that it disagreed with everything surrounding it, and for that reason alone, it was almost immediately dismissed. The value was not wildly divergent, not obviously nonsensical, but subtly off, positioned just beyond the comfortable boundaries where theory and observation typically aligned. This kind of discrepancy is common in scientific work, appearing frequently enough that dismissing it feels like prudence rather than prejudice. To understand why this measurement still matters today, we need to examine how certainty is enforced in science. Modern research depends on consistency, repetition, and agreement across methods, because isolated results are far more likely to be errors than revelations. Instruments fail, environments interfere, and human expectations shape interpretation. So skepticism becomes a form of protection. This is not unreasonable. The history of science is littered with measurements that seemed significant but proved spurious, artifact of flawed equipment or inadequate methodology. The default assumption that an anomalous result reflects measurement error rather than nature's truth is usually correct and has saved countless researchers from pursuing false leads. That protection shaped the response. The measurement emerged during routine analysis, produced by instruments that had performed reliably for years. Yet its value set just far enough outside expected limits to trigger doubt without triggering alarm. Analysts assumed calibration drift, statistical anomaly, or environmental interference, because those explanations had solved similar discrepancies countless times before. The value was noted, flagged for review, and set aside while other, more conforming data received attention. This triage was standard practice. Focus resources on results that made sense. Investigate anomalies only if they persisted or appeared in multiple datasets. As checks were repeated, the number refused to disappear. Recalibration produced the same result. Independent processing pipelines confirmed it. Even alternative instruments, measuring related properties, hinted at alignment with the disputed value. What was supposed to be an error began behaving with unsettling consistency. Each verification meant to eliminate the anomaly, instead reinforced it. The measurement appeared not just once, but repeatedly, not just in one dataset, but across multiple independent observations. The pattern suggested not malfunction, but genuine signal. Something real being detected even though it contradicted expectations. Still, resistance remained strong. Accepting the measurement meant questioning models that had been validated across enormous datasets, models that formed the backbone of entire disciplines. Rejecting it was easier, safer, and professionally comfortable. Outliers are expected to vanish under scrutiny. The models in question had been tested thousands of times, had guided decades of research, had enabled precise predictions and technological applications. They were not casual hypotheses, but established frameworks with proven track records. To suggest they might be wrong based on a single anomalous measurement seemed presumptuous, even reckless. The burden of proof for overturning established understanding is necessarily high. This one did not. As evidence accumulated, the measurement transformed from a nuisance into a threat, not because it was dramatic, but because it was persistent. It did not shout its significance. It simply continued to exist, challenging the assumption that disagreement always signals failure rather than discovery. Month after month, year after year, the measurement remained stable. New instruments produced the same value. Different research groups obtained consistent results. The statistical confidence grew as uncertainty shrank. What began as a probable error became an improbable but undeniable datum. As scrutiny deepened, the measurement became harder to dismiss without unraveling trust in the process itself, because every attempt to correct it produced the same stubborn result. Calibration histories were audited in detail, environmental conditions reconstructed, and statistical thresholds tightened. Yet the number remained unchanged, sitting just beyond the boundary of comfort. Investigators examined every link in the chain from raw signal to final value, searching for the error that would reconcile observation with theory. They found none. The measurement pipeline was sound. The instruments were functioning correctly. The analysis was rigorous. Either reality was producing this value, or some systematic error. So subtle, it evaded all detection was mimicking it. What made the situation increasingly uncomfortable was how well everything else behaved. Adjacent measurement aligned perfectly with prediction. Instruments showed no signs of drift, and noise profiles remained stable. The anomaly did not appear in isolation because of chaos. It appeared within order, precisely where error should have been least likely. This selective discrepancy was puzzling. If instruments were failing, multiple measurements should show problems. If methodology was flawed, errors should appear randomly distributed. Instead, one specific measurement persistently disagreed, while everything around it conformed to expectation. This pattern suggested not systemic failure, but a genuine physical effect that models had not anticipated. Discussion slowly shifted from whether the measurement was wrong to why it was wrong, a subtle but meaningful change. Some researchers suggested that the underlying model might be incomplete, missing a variable that only revealed itself under specific conditions. Others argued that the measurement exposed a hidden bias baked into assumptions that had never been tested because they had always worked before. This shift acknowledged implicitly that the measurement might be accurate, even while maintaining that its interpretation must be faulty. Perhaps the value itself was correct, but its meaning misunderstood. Perhaps it measured something real that simply did not fit the conceptual framework used to organize observations. As the debate widened, professional risk entered the conversation. Publishing a result that contradicted established understanding carried consequences, especially when the discrepancy was small enough to be dismissed as noise. Careers are built on reliability, not disruption, and the safest path remains silence or cautious framing. Junior researchers hesitated to champion the anomaly, fearing association with potentially embarrassing error. Senior researchers hesitated to stake reputations on overturning consensus based on subtle evidence. The incentive structure of academic science favored caution, incremental progress, and agreement with established frameworks. Bold claims required extraordinary evidence, and while the measurement was persistent, it remained small enough to question. Yet the data continued to accumulate. Follow-up measurements, taken months and years later, converge on the same value, shrinking uncertainty rather than expanding it. What once looked like a fluke began to resemble a pattern. And patterns are difficult to ignore without consequence. Meta-analyses combining multiple studies showed the effect was reproducible. The statistical significance crossed thresholds that normally compelled acceptance. The measurement's defenders could no longer be dismissed as outliers themselves. They represented a substantial and growing fraction of researchers working in the field. The deeper conflict was no longer technical, but cultural. Science depends on skepticism, but also depends on a willingness to let evidence challenge consensus. In that tension, the measurement lingered, waiting to be either buried or believed. The situation exemplified a fundamental dilemma in scientific practice. How much evidence is required to overturn established theory? Too little skepticism leads to acceptance of spurious results. Too much prevents recognition of genuine discoveries. The threshold is necessarily subjective, shaped by psychology, sociology, and institutional dynamics as much as by pure logic. The conflict reached its most uncomfortable stage when researchers realized that resolving the measurement would require choosing between trust in established frameworks and trust in the evidence accumulating in front of them, because both could no longer be upheld simultaneously. Preserving the model meant dismissing data that had proven remarkably stable, while accepting the data meant admitting that a cornerstone assumption might be incomplete. This was not merely intellectual discomfort, but professional crisis. Entire research programs depended on the validity of the models in question. Textbooks would need revision. Derived conclusions would require reassessment. The ripple effects extended far beyond immediate measurement. As discussions intensified, attempts were made to isolate the discrepancy, to frame it as a special case rather than a general problem. Papers were written that acknowledged the anomaly in footnotes. Presentations mentioned it cautiously, and explanations were offered that postponed confrontation rather than addressing it directly. The measurement was neither accepted nor erased, suspended in a professional gray zone. This limbo was uncomfortable but sustainable. The anomaly was noted without being emphasized, acknowledged without being explained, mentioned without being resolved. Science moved forward in other directions, while this particular puzzle remained unsolved. What made this moment particularly tense was how quietly disruptive the measurement was. It did not overturn theory outright or demand radical revision, but it nudged results consistently in the same direction, implying a systematic effect rather than random error. Small shifts, when repeated across independent studies, began to accumulate into something that could no longer be ignored. The measurement was not dramatic enough to force immediate reckoning, but persistent enough to prevent comfortable dismissal. It occupied that awkward middle ground where ignoring it felt intellectually dishonest, but addressing it required uncomfortable effort. Behind closed doors, confidence in long-standing assumptions began to erode. Researchers questioned whether previous results had been subtly influenced by the same overlooked factor, masked by uncertainty and averaging. The possibility that an entire body of work rested on a shared blind spot was unsettling, because it suggested that agreement itself could be misleading. If multiple studies agreed not because they were correct, but because they shared the same unexamined assumption, then the consensus was hollow. This realization struck at the heart of scientific validation. That reproducibility and agreement among independent researchers constitutes evidence of truth. In this phase, the measurement stopped being about a single number and became a referendum on how science handles discomfort. The conflict was no longer between right and wrong, but between familiarity and curiosity, between preserving coherence and allowing complexity to reshape understanding. The measurement became emblematic of broader questions about scientific culture, methodology, and epistemology. How should science respond when evidence contradicts consensus? When does healthy skepticism become obstinate resistance? How much should past success influence present judgment? The question looming over the field was simple and dangerous at the same time. What if the measurement was not wrong, but early? What if it represented the first glimpse of a phenomenon that models had not anticipated, a signal from territory theory had not yet explored? The possibility that the measurement was not error, but discovery transformed its significance entirely. If true, it represented not failure, but opportunity, a chance to extend understanding beyond current limits. The climax of the story arrived when the weight of repetition finally outweighed the comfort of dismissal, because the measurement had persisted across methods, instruments, and time without drifting toward expectation. What was once treated as an inconvenience became impossible to ignore, not through drama, but through endurance. The tipping point was not a single definitive experiment, but the accumulated weight of consistent replication. Eventually, the improbability of systematic error became greater than the improbability of the measurement being genuine. Acceptance did not come as a declaration, but as a shift in language. Papers began to frame the value not as an error, but as a discrepancy. Models were adjusted cautiously, not rewritten, allowing space for the possibility that something subtle had been missing all along. The measurement did not overthrow understanding, but it forced it to bend. New theoretical work explored mechanisms that could produce the observed value. Experimental programs were designed to probe the effect more thoroughly. The measurement graduated from anomaly to phenomenon, from problem to research agenda. The resolution revealed something deeper about progress itself. Science advances not only through bold discoveries, but through stubborn details that refuse to disappear. This measurement mattered because it was small, because it hid inside precision, and because it challenged the idea that consensus always signals completeness. It demonstrated that truth sometimes arrives quietly, that significance does not require drama, and that persistence can be more convincing than spectacle. In hindsight, the resistance made sense. Accepting the measurement meant admitting that familiarity can blind even the most careful observers, and that agreement can sometimes amplify shared assumptions rather than expose them. The universe had not changed its behavior. Our interpretation had. The measurement was always accurate. The frameworks used to interpret it were incomplete. This is a humbling but essential lesson, that scientific understanding is always provisional, that models are approximations, and that nature reserves the right to surprise those who look carefully enough. Today, the measurement stands as a reminder that discovery does not always announce itself with spectacle. Sometimes it arrives quietly, survives doubt, and waits patiently for understanding to catch up. And when it finally does, the shift is not explosive but transformative. The measurement that everyone thought was wrong became the measurement that revealed how much remained to be understood. It taught not just new facts, but new humility about the limits of certainty and the value of persistent evidence. Sometimes the smallest shift in perspective becomes the beginning of a new future. And sometimes that shift is recognizing that what everyone agrees is wrong might actually be the first sign of what no one yet understands. The